Welcome to my video on permutations versus combinations. I'm going to start with permutations because I think those are actually easier than combinations. At least the way you derive the formula is easier. Let's think of a quick example. Let's say you have 6 objects. Actually, let me make 6 distinct objects. They're not the same. And you have to arrange them into 4 spaces, and order matters. So for example, say you had these 4 spaces, and this is so 2, 1. If you were to order them like this, say you were to order it like you put the 6th object here, the 4th object here, the 5th object here, and the 1st object here, that is different than if you were to switch these 2 around. So if you switched around 5 and 1 and you did instead 1 and 5, those are different cases because the order matters. So let's see how many ways you think we could do this. So how many ways can we arrange 6 distinct objects into 4 spaces where order matters? Well, in the first position you have 6 choices. In the second position you have 5, then 4, then 3 choices, and that will give you a grand total of options of 6 times 5 times 4 times 3. And I don't really care what that number is. What I want to show you is that this actually equals 6 factorial over 6 minus 4 factorial. Because 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1, if you please. And 6 minus 4 factorial, well, that's just 2 factorial, so that's 2 times 1. So if you were to divide these guys, you'd get, so 6 factorial divided by 2 factorial, which is 6 factorial over 6 minus 2 factorial. What you're going to get is you're going to get 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1. These 2 cancel, and you're left with 6 times 5 times 4 times 3, which is exactly what we expected from our answer. So, in general, when you're talking about permutations, if you want to order matters, and you want to choose k objects from a pool of n objects, then I believe it's n permutate k. I believe that's, yeah, this is definitely it. N permutate k is equal to n factorial over n minus k factorial. So if instead you were choosing, say you had 8 objects and you needed to fit them into 3 spaces in the order matter, well, that's going to be 8 factorial over 8 minus 3 factorial. This is 5. So this is 5 factorial. So this is going to give you 8 times 6 times, oops, not 6, 8 times 7 times 6. And the 5, 4, 3, 2, and 1 is going to cancel. Okay. So that was when order mattered. Order matters. What if order doesn't matter? Then we're dealing with a combination. So this is a combination, is the same exact thing. Say you have 6 distinct objects and you have to arrange them into 4 spaces, but the order doesn't matter. Clear this. Combinations. You have n distinct objects and you want to, I don't know. A classic way of thinking about this, well, before I finish this, the classic way of thinking about combinations is you have like a classroom full of people, and the teacher just puts you all into groups. So he puts them into groups, that into a group, that into a group. And so like say there's like 10 students. I don't know, actually I'll just say there's 12 students, and he puts you into groups of 3. The order he selects you doesn't matter. The only thing that matters is what group he puts you into. Assuming that every group member has the same like position. Okay, let me erase that. So back to the definition. You have n distinct objects and you want to choose k of them. So, and the order in which you choose these objects does not matter. And of course, this is without replacement as well. So once you choose an object, you can't choose it again. So you have n objects and you have k spots. So here's your k spots. You have spot number 1, I'll make this a little neater. You have spot number 1, spot number 2, spot number 3, spot number 4, spot number k. And let's say that you choose, so you pick from this pool of n objects, and n of course is going to have to be greater than or equal to k, because then if n wasn't greater than or equal to k, then you would run out of positions before you got to the end, and that wouldn't make a whole lot of sense. In which case, I think the answer would be 0, but don't put too much thought into that. With the combinatorics we're dealing with, we're going to be dealing with the cases where n is greater than or equal to k. We're not worried about the cases where n is less than k, so don't worry about that. So let's say you chose, I don't know, let's say you put 2 here, 3 here, n here, 1 here, and I don't know, 7 here. And you've come up with an arrangement of these objects. Remember, the order doesn't matter. So if I were to switch, so let's say if I were to switch 2 and 3, and I put 3 and 2, I don't want to count that as a separate case than what I had before, because then I would have overcounted by 1. So it looks like so if the order didn't matter, the number of ways we could do it, number of ways we could order these would be just n factorial over n minus k factorial. That's all there would be. That's it. But the thing is, we could overcount. So this is an overestimate. How much do we overestimate by? Well, I'm going to claim that we overestimate by a factor of k factorial. Let me show you an example of this is the number of ways we order. This is the actual answer. I'm going to explain why you have overcounted by a factor of k factorial. So let's say you have person A, B, and C, and you want to order them. I'll actually do it with A, B, C, and D, and you want to order these people into 3 spots. So let's say you put A here, B here, and C here. Well, as I said before, since the order doesn't matter, that's the same as putting B here, C here, and A here. As long as there's no D, as long as you have all the same objects, the order doesn't matter. So these are the same cases. Well, how many ways can we come up with these? Well, in the last video on factorial, I showed you that there are 3 factorial ways you could arrange them. So you have effectively overcounted by the number of spots factorial. So if you had k spots and you had a particular arrangement, 1, 2, k, then you will have overcounted by k factorial if you apply the permutation formula, because that's the number of ways you could rearrange all of these people and it wouldn't make a difference. So this is the number of ways we could order, and this is also called n choose k. That's the way you can write it. Just these long parentheses and n on top of k. So let me just do a quick review. N permutate k is equal to n factorial over n minus k factorial. And the order matters. And n choose k is the same exact thing, except you overcounted by a factor of k factorial. And here the order does not matter. Okay, we are ready to now move on with the playlist and show how we can derive a formula for sigma 2 of n, and how we can find a formula for this using something called the hockey stick identity. So if you take nothing away from this video, just take away this formula because we're going to be using it in the next video. See you there.